Okay. Okay. Yeah. Thank you very much. Today I will be covering mostly on the sustainability concerns, which is due to climate emergency or climate crisis, or any kind of climate related impacts, how we can mitigate and adapt to this evolving problem. So basically, I will be discussing more on an integrated approach where all this climate system functions together as an internal system. So what is required is we have to consider the climate system as a whole, means like an integrated system. So it composes of nothing but most of this climate system, which is the energy is mostly coming from the sun. So with that energy, so with sun's energy, all our internal climate system is working together, which includes atmosphere, geosphere, including lithosphere, hydrosphere, including ocean, and then biosphere, including man and other animals, and maybe the flora and fauna. Or so the entire system is functioning based on the received energy from the sun. So that is why sun is considered as a external forcing for the climate system. So the internal feedbacks are nothing but the feedback and energy exchange, the fluxes of mass and energy between all these spheres. So that makes the stability of the climate system, Earth climate system. So if there is any changes in any one of the spheres, it will affect each other, and so that is what the mostly anthropogenic activity is changing atmosphere, our lithosphere and biosphere, and partly the hydrosphere as well. So in effect, the entire climate system feedback, everything will be affected, and that is leading to the climate change, or what you can say the present global warming. So the outline of the talk, which covers briefly on little bit on the science of the climate change and why we need to know about the past climate of Earth, and then what is happening now, and then how the future projections look like. So this is how the climate science works. We need to know how the Earth climate have evolved over the period. So the climate of the Earth never remains same over a period of many years. So it is continuously evolving. So that how that had happened in the past, and how what is the scale at which it is happening at present, and what we are expecting for the future. So this is how the climate science works, and what are the impacts. So impact is the global warming induced the extinction crisis. That is, the extinction means the existence of the human is also very under threat. So in the present, if we consider the present warming rate, and then what are the impacts of this climate change, and how we can mitigate, and immediately how we can adapt to these changes, and then the long term how we can mitigate, and then in the integrated climate action, because climate action is included as one of the major SDG goals in the UN framework. So anyway, the climate action is very much important. So I will briefly touch upon that as well. So this is the outline. We know that the science is evolving, because it is not just the truth. Science is nothing but the finding out the truth through some methodological pathway. So if you look at the evolution of the science, we know that during Aristotle and Ptolemy time, they proposed like a Earth-centric, geocentric overview of the universe. So considering that though they were great philosophers, they were thinking that Earth was the center of the universe. But later, when Copernicus and Galileo came, so they established that the center is of our universe is not the sun. The sun is just even Earth is one among the planet, and sun is center of the solar system. So that is how the science is evolving. It is not just the truth remains as a truth, but the science helps us to find out the truth, because for the last 4.56 billion years, this is the truth. But it came, we came to know this truth very recently, maybe in the last 600, 800 years, or maybe less than that. So that is what the science is evolving. So if you look at the climate system, as I told, Earth is situated at the third position from the sun. So that is the main reason why we have life only on the Earth. It is not just about the distance between the sun and the planet, which determines the uh, conducive atmosphere or the conducive climate uh, for the evolution of life on the earth. It is because of the presence of the water, and that water is mainly found in all three forms over in earth. So only in earth. So if you can find water in Mars, but maybe in a frozen form, maybe in the Venus it can be in the vapor form, but in the earth, or over the earth, we can find water in all three forms. So that is the temperature, that is the unique temperature. So that unique temperature, which is actually making our planet as a blue planet. If you look at the false color image, you can easily identify Earth apart from other major planets. So it is mainly because of the presence of the water and the presence of the ice. So that makes the difference. So how this evolved? So it is mainly because of two factors. If you look at the Goldilocks, how that Goldilocks equilibrium temperature arrived. If you look at the main energy source, sun. So then derive that theoretical temperature of or equilibrium temperature of Earth from the Planck's law, that is a commonly the common radiation law. So that, based on that, we have different variants of this Planck's law, like Stefan's Boltzmann, Wien's displacement law. So based on that, we can arrive at a equilibrium temperature with this equation. So it is actually equating to the energy. How much is the energy received at the top of the atmosphere, and how much is the energy going out of the Earth. So this two in balance, that makes that equilibrium temperature. So if you equate that, we can find that equilibrium temperature is a function of solar constant x0. x0 is nothing but a solar constant, or the solar irradiance, which is reaching at the top of the atmosphere. So then there is a function called A. A is nothing but the albedo. Albedo is nothing but the reflective property of the any planet system, the climate system of any planet. So that means when we consider the total available energy which is available to heat up the planet, so out of the incoming solar radiation, A amount of this incoming solar radiation is reflected back. That leaves 1 minus A into S. That is the available energy to heat up the planet. So then this planet absorbs all this energy, that 1 minus A into S0. So based on that energy, the planet again re-radiate energy back to the atmosphere. So this energy which is coming from the sun to the earth, which is mostly in the shorter wavelength, it's a short wave energy. And once it is also depending on the Planck's law, because sun's photosphere temperature is around 6,000 Kelvin. Based on that, the peak emission is happening somewhere around 0.5 micrometer. So it is near to a green wavelength. So that is why it is most of the sun's energy is coming in the shorter wavelength, and then the earth absorbs this energy based on this earth temperature. Earth's temperature, average temperature is something around 300 Kelvin only, and that means displacement, which is in the wavelength of the emitted radiation, is inversely proportional to the temperature. So that means if temperature is less, the emitted wavelength will be larger, longer. So that is why Earth emits radiations in the infrared region, in IR rays. That is why it is known as thermal radiation or infrared radiation. So incoming solar radiation is mostly in the visible and near infrared. So maybe 5% is coming in the ultraviolet region as well. So the Earth radiates back. So if there is no atmosphere, or if there is atmosphere without any greenhouse gas or carbon dioxide, all this energy will be escaping back to the space, and so that there won't be much energy is available to heat up the Earth. So in the presence of greenhouse gas, which is represented by the letter epsilon means so the part of this based on the absorptivity capacity of the atmosphere, part of this outgoing long wave radiation is getting absorbed by the greenhouse gas and then re-radiate back to the earth atmosphere, so that will keep our earth warm to a warmer temperature. So that is what if you look at this equation, so epsilon is coming in the denominator, sigma is Stefan's Boltzmann's constant, but epsilon 1 minus epsilon means if epsilon is large means 1 minus this quantity will be small, so that temperature will be high. So that is the relationship. So it's a fundamental first order relationship between the incoming solar radiation and outgoing terrestrial radiation. So based on that, we can derive the thermal equilibrium temperature of any planet. This is the case of any planet. So you can derive the equilibrium temperature of Mercury, Venus, Earth, Mars, or whatever planets you want to do. So that is why if you look at compare the temperature, consider here we are considering a theoretical case where there is no atmosphere. So in that case, if you look at the temperature, if you compute, in that case here epsilon will be 0, it will be just S0 into 1 minus A divided by 4 sigma, because epsilon is 0, there is no atmosphere. So in that case, if you calculate the equilibrium temperature of Mercury, it will be something around 163, and Venus it is minus 41, but Earth it is minus 18. How it can be? So because Earth is coming at the third position after Venus, then why the equilibrium temperature of Earth is minus 18, larger than higher than the Venus? It is mainly because the quantity, the albedo, because the albedo fraction means the albedo of Venus is 0.7 or 0.77. 77% of the incoming solar radiation is being reflected back in the case of Venus, but in the case of Earth, the albedo is 0.3. That is why only small amount of radiation is being reflected in the case of Earth. That is why if we don't consider atmosphere, the Venus temperature would have been minus 41 and Earth temperature is minus 18. So that is mainly because of the higher albedo of the Venus. So, but in reality, Venus temperature is much higher. So if why so? Then we add, if this is a theoretical case where no atmosphere is considered, when we add atmosphere to each planet, then you calculate the observed temperature. Mercury temperature will be something close to the theoretical temperature, 167, close to 163, because Mercury doesn't have a very rich atmosphere, very thin atmosphere. But in the case of Venus, it changes from minus 41 to 462, almost like 500 degree Kelvin increase in temperature is observed in Venus atmosphere. That is mainly because of Venus contained a very thick, dense atmosphere. If you look at the atmospheric pressure, it is almost like 9300 kilopascal. If you look at the atmospheric pressure of the Earth, it is just 100 kilopascal. So 100 times more kind of atmosphere supported by Venus, in which carbon dioxide concentration is almost like 0.96. That means Venus atmosphere contains 96% of the carbon dioxide. So, but in the case of Earth atmosphere, it is mostly nitrogen, oxygen. The carbon dioxide is and other greenhouse gases by concentration, it is less than 1% altogether. So that is that optimum concentration of the chemical species in the atmosphere. That is the main reason for this optimum or the Goldilocks temperature, which we have found over the found in the case of the Earth. So that equilibrium temperature, that optimum or Goldilocks temperature, that is the main reason for Earth having the water in all three forms. Because if you look at the triple point of the water, it is close to it is somewhere very within the temperature ranges which is naturally observed in the Earth atmosphere system. So that is the main thing which makes Earth as a unique planet with optimum amount of chemical species in the atmosphere that supports all other activities. So that is the main reason for this present day temperature of the Earth. So that is the main reason for all other processes which is happening, or the evolution which happened over the earth, that made the presence of life due to the presence of the water. So that is the main reason. So if you do, this is just a comparison between Mars, Earth, Air, and the Venus. So it's a general comparison. So, and this is already I discussed. If there is no greenhouse gas, Earth temperature would have been 256 minus 18 or minus 16. So if we add atmosphere theta epsilon to 0.75, so then only the equilibrium temperature will remain like this. So that is the main. So through equations and through theory we can establish this. So that is why if you look at the evolutionary history or the geological evolution of the Earth, we can find that Earth came into existence maybe 4.56 billion years back. And then after that, the temperature of the Earth would have been very higher, and it cooled down after all kind of bombardment and the collision with other asteroids and meteors, and then it came down, temperature came down to below 100 degrees Celsius. So that time, whatever water vapor available in the atmosphere might have condensed and formed the vast ocean. So this is how the evolution has happened. From that point onwards only, that after that prokaryotes formed, then maybe initially they lived with the energy which is available naturally, like thermal vents and all. So then after that, they increase in population, and there was not enough energy to sustain. So they find out another way to sustain. It is nothing but the photosynthesis. So that is also a chemical reaction where, in the presence of sunlight, it consumes most of the carbon dioxide present in the atmosphere, and then as a byproduct, that is the main carbohydrates, the energy source which is provided, and as a byproduct, oxygen is liberated in the ocean first, and the oxygen is then liberated to the atmosphere. That was that time, almost like between 2 and 1.5 billion years. That period is commonly known as oxygenation period, or the great oxygenation event. So it is a kind of holocaust where the species, especially the prokaryotes, maybe the eukaryotes, they were not the process is not that aerobic, so that might have created some issues during those period. And then carbon dioxide, oxygen, because that's a chemical evolution. If you look at the chemical composition of the Earth during the time Earth formed, it is carbon dioxide dominated atmosphere, water vapor dominated atmosphere, and it came down drastically in last maybe after 2.5 billion years, and then oxygen came to the atmosphere, and that created a lot of changes in the flora and fauna, or the entire biosphere of the atmosphere Earth has been changed due to that, and that is where we are living now. So this is why the chemical evolution, what is the reason for the first form? It is generally believed that it is through chemical evolution from the from in the ancient period, that was established. So that is what, if you look at the climate change as a whole, there are many. Also, if you look at if you look at the history of in the geological history of the Earth, the Homo sapiens, they lived in just maybe less than 0.1% of the entire period of the Earth history. So that means we are negligible in the case of whatever happened in the past, and that is mainly because of the natural factors. If you look at the climate change due to natural factors, there are many reasons for that. That is why I already mentioned that Earth climate never remains same over longer period. So it is naturally, as I told in the equation, whatever changes contributed to the change in the solar constant, that is though it is an external factor, the changes happening in the solar sphere, it can have the impact in the Earth temperature. So because if you look at the period when Earth formed 4.56 billion years back, the Sun was emitting almost like 30% less energy compared to what Sun is emitting now. So that means that is why there is a famous saying that faint young sun paradox, where the solar constant was less at that time. So the part of that, as I already mentioned in the case of Venus and the Earth, the albedo difference, the higher albedo in the Venus is being compensated with higher concentration of carbon dioxide in the atmosphere. That is why Venus temperature is more than the Earth temperature and more than the Mercury temperature. So here the solar constant is very much important. It was not it never remains same because it is evolving at a scale of like billions of years, where we had 30 percentage, Earth received 30 percentage more energy when Earth was formed. That is why, due to faint young sun paradox, part of this less energy input from the sun is being compensated with higher concentration of greenhouse gases. Not only carbon dioxide, the atmosphere of the Earth might have composed of a lot of water vapor those time. So the combined effect of water vapor in the atmosphere and carbon dioxide and other greenhouse gas, that compensated for the low energy input from the sun. So this is how the theory is telling how the system is evolving over the time. Then another natural factors which is linked to the Earth orbital cycles, like it is collectively known as Milankovitch cycle, which is related to the tilt of the axis revolution, or means orbit of the Earth around the sun, and then inclination or the position of the Earth axis. So these are the three things which determines the orbital properties, which would have a impact on the Earth temperature and Earth climate. So that is happening over a time scale of like 25,000 to 1 lakh years. That is collectively known as Milankovitch cycle. So that is the main reason that scientists found out that that is the main reason for this glacial interglacial cycle, which is happening at a regular interval of like say 75 to 1 lakh years. So then volcanic activity, that is also a natural factor. Due to this volcanic activity, what is happening, mainly if you look at the equation, due to volcanic activity, the epsilon will be changing because it is more related to the atmospheric property of the Earth, where more and more greenhouse gas or aerosol particles will be ejected to the atmosphere during a volcanic eruption. So where, depending on the characteristics of the particles which is being ejected, it can have both effects, like during a volcanism, sometimes due to volcanism, the Earth might have gone for a large scale cooling that led to a snowball kind of Earth situation, where all water from the polar to the subtropics cooled down below 0 degrees Celsius, where all water is freezed. So that is what a case where happened in the geological past, where, and sometimes if volcanic activity eject more greenhouse gases, then what happened is that it will have a warming effect due to higher greenhouse gases. So these are some of the natural factors which created lot of changes in the Earth climate over billions of years. So then the main another factor is like the tectonics. So that is the main another geological factor which determine the climate of the Earth. So the present climate of the Earth is mostly determined or means stabilized due to the plate tectonics. So if you look at that, that is what Earth has undergone through a kind of supercontinent cycle, where earlier it will continent will merge together, then split up, then merge together. This is known as supercontinent cycle. So a very recent supercontinent was the Pangea, which was maybe 250 million years ago. And after that, Pangea split into Gondwana and Laurasia. Then within 150 million years ago, around 15 crores of years ago, and by between 150 and 100 million years ago. So all this, we were actually close to India, was close to Africa, Australia, Antarctica. Just imagine how could have been our climate maybe 10 crores of years back, 100 million years back. But just imagine that. So that is why, and then India started moving towards north and collided with Eurasia, formed the famous features here, the Himalaya. So that is why, due to this subduction of this Indian plate towards the Eurasian plate, that leads to the upliftment of the Eurasian plate along the margin. That is where that region is tectonically active, and you can find most of the earthquakes over that belt. So that is the main reason. And then if you look at the height of the Himalaya, it is increasing because now also this plate tectonics is active and happening. Like every year, plate is moving like millimeters per year, and that leads to the upliftment of kind of Eurasian plate. That leads to the increase in height of Himalaya over the years. So this plate tectonics is the main thing. So otherwise, if you look beyond 100 million years back, Earth climate which we experiencing all over the continents was not same as we are experiencing today. So that means our present day climate has a very less history, or the very less history, less than 100 million years of history. So that is the main reason. So what we are experiencing now is just we are experiencing for the last Earth is experienced for the last 100 million years. So due to that, when it comes to our climate, like for example, the Madagascar island, which was close to Indian plate, sandwiched between Africa and India, during the Indian plate movements towards the north, Madagascar remains in the Southern Ocean, and that still remains there. But still, we can find a lot of resemblance between Western Ghats and the part of the landscape in the Madagascar, and also the lot of freshwater species, the pear spot or the Etroplus surantensis, the famous the carimine of this backwater freshwater species is abundant in Sri Lankan freshwater, Kerala freshwater, and the Madagascar freshwater. So there are a lot of resemblance in the flora and fauna as well. So this is the reason for why India is having the monsoon, because if you look at this unique geography, the unique geographical positioning of the India or the South Asia with respect to ocean, especially South Indian Ocean. So that is the main reason for the monsoon to occur over our domain. And if you look at the January wind pattern, we can find that in the Pacific it is easterly, and in the Atlantic also it is easterly, but in our Indian region it is northeasterly. That is why during those periods it is known as northeast monsoon. And after 6 years later, in July, the wind takes a U-turn. So almost like coming from it starts from this region, the Madagascar or the subtropical high region in the southern hemisphere, close to Madagascar, east of Madagascar, and that is why it is starting. The monsoon wind actually start close to Madagascar and coming from the southwest direction towards Indian land. That is why it is known as southwest monsoon. So this reversal of wind is happening only over the South Asian domain, over this domain. That is why we are unique. That is why we have the unique monsoon system over the Indian domain. Otherwise, if the wind pattern in the Pacific during these two periods, it is mostly easterly during those two periods. So only over India, this 180-degree turning of the wind is happening. That is where we have the monsoon. That is mainly because of the unique orientation of this entire South Asian landmass with respect to the ocean. If you look at the Pacific, there is no landmass here, and if you look at the Atlantic, there is no landmass here. So that is why this geography, unique geography, is the main reason for the monsoon to exist over the South Asian domain. So, and if you look at in a large scale perspective, if you look at the general circulation of the atmosphere and the climate, we can find that most of our perpendicular direct sunlight is falling in the tropical region. Tropical region is nothing but the 23.5-degree north and south region, this belt. Most of the sun's energy, most of the time sun's energy is falling within these two latitudes. So it means mostly energy density is more in the tropical belt, and that is why if you look at this, our tropical belt the sun's energy is falling perpendicular, but when it comes to the polar region, it is falling slanting, so that the energy density. So that is why if a same amount of 1 kilowatt per meter square energy is falling over 1 meter square, energy density is more. But the same amount of energy distributed over 2 meters square, the energy density will be less. That is happening here. Here, energy density is more, here, energy density is less. And that energy gradient, that thermal gradient, that is the main reason for all activity which is happening over there. So that is what the feedback mechanism. So if you look at the energy gradient or the energy difference between the tropical region and the polar region, we can find that if you look at the incoming solar radiation, so it is distributed with respect to latitude. It's a very large function of latitude, because as we move away from the equator, as the latitude increases, the energy density decreases, because that is directly as a direct function we can find. But when it comes to ongoing long wave radiation, if you consider sphere, only pi r square area is being intercepted with the sun's energy, but this intercepted energy is distributed throughout the Earth atmosphere, so that the outgoing long wave radiation is not just from the tropics, it is almost uniform from everywhere. So that is why if you look at the incoming radiation distribution, this is latitude towards the south and north, the distribution of incoming solar radiation is like this, and outgoing long wave radiation is almost uniform across latitudes. That leaves surplus energy, because if you take the net energy availability, tropical region will have a surplus amount of energy and polar region will have a deficit amount of energy. That is the energy gradient. That energy gradient is the main reason for our all atmospheric circulation, ocean circulation, all this activity is happening. That is why that is the main reason we have to consider Earth as a system. So all this energy exchange is happening through atmosphere, through ocean. Lithologically or the geologically it is not happening much, but otherwise there is local interaction is happening. That is why as a climate system we have to consider climate as a integrated system, including lithosphere, atmosphere, hydrosphere, biosphere, including us, all life. So that is the climate system. There is constant exchange of energy and mass between all these spheres. So that exchange of mass and energy is through different many processes. So I am not able to list out all these processes, non-linear processes, because these are the main non-linear processes through which only this energy exchange between polar region, tropical region, through atmosphere and ocean is happening. So this is a highly complex non-linear system. And coming to the temperature changes and the carbon dioxide changes over the last 4 lakhs of years, 400 into kilo years. So if you look at the last 4 lakhs of years, temperature evolved like a glacial interglacial cycle. So it was happening like this. So now we are in an interglacial period. So this periodicity between one glacial cycle to another glacial cycle is, as I already told, it is between 75,000 to 1 lakh years. So this is closely associated with the Milankovitch cycle, which I have already mentioned about, which is linked to the Earth changes in the Earth orbital properties. So that is happening over a periodicity of 75,000 of years. So that is happening every 75 to 1 lakh years. So that's why in the last 4 lakhs years we witness almost like 4 glacial interglacial cycle. Along with that, I have plotted the carbon dioxide variability also. This is also synchronized with temperature variability. So that means the temperature variability has got a close association with the carbon dioxide variability. So it is not very difficult to say that whether carbon dioxide is driving the temperature or temperature is driving the carbon dioxide. That they are closely synchronized. If you look at the variability, they are very much synchronized. So what I want to say from this image is that if you look at the last 150 years and you just take this violet line, So this violet line is considered as the natural threshold limit of carbon dioxide in the atmosphere. Though the carbon dioxide, this is the scale of carbon dioxide in ppm. Between a glacial and interglacial period, it is varying from 200 to 300 ppm, but never close to 300 ppm threshold limit. So now in the last 150 years, it crossed the 300 natural threshold limit, and now it is almost like 427 ppm. 127 ppm increase happened in less to 150 years. And if you look at the last glacial interglacial cycle, though 80 to 100 ppm variation is happening, but it is happening over a period of like 1 lakh years. So that periodicity is very much important, and that rapid rise in carbon dioxide in the last 100 years after industrialization or the industrial revolution. So that is the main reason for, because all our activity, economic activity is directly linked to is driven by fossil fuels. So that is the main reason for this rapid increase in carbon dioxide concentration and also the temperature of the Earth atmosphere system. So this is another way of describing it. We can get the proxy data or the AICTE data for the last 8 lakh years. That is the maximum we get from the AICTE information of the Earth climate from the AICTE. So that is also, if you look at the methane concentration and the carbon dioxide concentration, it is very high in the last 150 years. So this is the evidence of climate change and the global warming. Keating, he started observing this carbon dioxide in Hawaii Beach with instruments. So he found that is why this curve is known as heating curve. So when we talk about climate change or the global warming, everybody talk about the carbon dioxide and this variability, but in terms of energy, it is actually the Earth energy imbalance. As I told, in order to have equilibrium temperature, incoming radiation and outgoing radiation should be in balance. That lead to a equilibrium temperature. If they are not in balance, if something is changing within the Earth system, it may not be getting balance. So that imbalance in the energy exchange is actually the main reason for the climate change or the global warming. So that energy imbalance, how much is that? If you look at in terms of unit, if you look at 340 units of energy or 340 watts per meter square energy is coming at the top of the atmosphere, which is being distributed within the Earth atmosphere system through various processes. But that leaves nowadays almost like 0.9 watts per meter square positive energy, positive net energy within the Earth climate system. So that is the main reason for the global warming. So if you just compare, you may not be getting that feeling. If you just compare this energy, how much is this energy? Almost close to 1 watts per meter square energy is almost like, and if you, this is available at every meter square on the Earth's surface. If you consider the entire surface area of the Earth, it will leads to like 500 terawatts of energy, instantaneous energy. So if you just compare the 2018 global energy generation, it is just for 5.7 terawatts. So it is almost 100 times more energy is equivalent to 0.9 watts per meter square energy. So that is huge. So that much energy. In another way, you can say that we can, if it is close to 1 watts per meter square, we can light up 1 watts LED bulb at every meter square area on the Earth's surface. So every instant, every time, 24/7. So that is the concept of this energy imbalance. That energy imbalance is the main reason for that changing the equilibrium temperature. So that is why temperature is increasing due to this energy imbalance. So in terms of carbon dioxide, if you look at that carbon budget, we can find that through all our activities, almost like 9 gigaton carbon is being ejected to the atmosphere. It is almost equivalent to almost, when we factor oxygen O2, it is almost like 38 to 40 gigaton carbon dioxide equivalent. So out of that, our ocean is absorbing 2.6, and our entire terrestrial land, including the tropical forest and all, they are absorbing almost 2.9. So that leaves almost like 4.5 gigaton carbon in the atmosphere every year. That is the annual carbon budget. So that is might have changed. Maybe it is taken 1 year back. It might have changed little bit, but otherwise, every year we are dumping almost like 4.5 gigaton carbon, almost like 18 to 20 gigaton carbon dioxide to the atmosphere. That is why you always get this type of hockey stick type of curve in terms of carbon dioxide concentration. So this is how the carbon budget, if you want to reduce this global warming, you have to we have to achieve that net zero target, like whatever is emitted is being absorbed, or for that that is what the concept of net zero is coming, or carbon neutrality what we talk about. So our ultimate aim in a mitigation perspective is to achieve that net zero. So that is, to achieve that net zero means we have to reduce either our emission, or we have to implement a lot more sequestration facilities to sequester most lot of carbon dioxide from the atmosphere. So we can establish, because this is theoretically proven, that anthropogenic activity is the main reason for this recent increase in carbon dioxide in the atmosphere, mainly because of the fossil fuel driven economic growth, where we are dumping, we are igniting more and more fossil fuel for our economic growth. So that how we can establish scientifically that due to this anthropogenic activity alone is the main culprit of this global warming in the recent times. For that, one way to do that is with a mathematical model, climate model. We can replicate, simulate the climate of the Earth through mathematical models. So in that we use different type of forcing, as I discussed in the first or second slide, that sun is considered as an external forcing to the Earth climate system. So if you in our model, if you consider only natural forcings, like whatever natural forcing I have already discussed, like Milankovitch cycle, volcanic activity, solar luminosity changes, we consider only those, and then we run the model. So this red color is the temperature anomaly with respect to a baseline period of 1850 to 1900. That is considered as the pre-industrial baseline period temperature. And if you look at that observed temperature, it is almost like, now it is almost like 1.2 degree warmer by 2020, but it is much updated now. And when we run our model only with the natural factors, natural, we are not including any human activities, then it will come, some anomaly will be coming something like 0.2 watts per meter square only. So this excess 1 watts per meter square, when we run our model by including human activities, anthropogenic activities along with the natural factors, then only we will get to that observed anomaly very much close to, or it is following almost close to the observed temperature anomaly. So this way we can prove that with a mathematical model, because as I told, the temperature, equilibrium temperature change, that is a first order equation through which we can establish that. So there we can find that through mathematical models, we can find that the present day change in temperature increase is mainly because of the natural factors. Other way to find out this is that if you consider the Earth system, ocean is very much important, because ocean is important in two factors. Because if you look at the total mass of the ocean compared to the atmosphere, something like ocean heat capacity is 3 orders of magnitude. This is 10 raised to 24 joules per Kelvin magnitude, and the total mass is also something like 3 orders of magnitude greater in the case of ocean. So the total mass along with the specific heat capacity, that is 4 times more compared to the atmosphere. So this all together putting ocean absorbing more and more heat energy compared to the atmosphere due to the large mass and the large specific heat capacity of the water. So this is how, if you dump more and more heat to the atmosphere, 93% of this heat is being dumped in the ocean. So that is clear, that is theoretically proven. And another factor why ocean is important is that it is absorbing almost like 25 to 30% of carbon dioxide. Just leave it that for the time being, but otherwise ocean is absorbing the 93% of the heat which is liberated to the atmosphere. So then, if we measure the ocean heat content over the last maybe 30, 40 years, so this ocean heat content itself, increase in ocean heat content itself will clearly establish that our atmosphere is warming. So globe is warming. So this way, through satellite data, we can compute, we can estimate the ocean heat content, which is also increasing over the years. Now it is almost touching 1.2 watts per meter square. This way also we can establish, measure the change in Earth atmospheric temperature over the years. So this is another way of establishing that, and then due to that, climate change is happening because this is a very serious issue. Because if you look at the climate system, if there is no ocean, so ocean is actually buffering the ill effects of all climates. If there is no ocean, then all this energy will be available to heat up the atmosphere and the land. So the temperature would have been much higher. The global warming would have been much rapid and higher if ocean is not consuming this much amount of heat energy and carbon dioxide. But ocean is doing this at the expense of suffering the marine ecosystem, because the ocean is buffering the worst effect of climate change at the cost of significant harm to marine ecosystem, because warming along with the less oxygen, because oxygenation, hypoxic region is increasing over the global ocean, and ocean water is getting more acidic. Due to that, there are a lot of issues we are finding over the ocean. It is sea level rise, coral bleaching, toxic algae blooms, habitat loss, acidification, and reduction in the fisheries productivity, fisheries fish potential. So these are some of the ill effects due to climate change, especially in the ocean marine ecosystem. And then that is why we have to consider, apart from the previously considered the spheres, which in which the man, human is considered as part of the biosphere. Now human is considered as outside the biosphere, where there is a anthrosphere, where human can influence all other spheres. Like we can, means man can change the lithosphere, land surface, and man is changing the atmosphere, man is changing the hydrosphere, and man is changing the entire biosphere by killing the species. So that is why the anthrosphere is that's why this era is otherwise known as Anthropocene, but it is not true, because if you look at the Anthropocene, the global population is already touched 8 billion. So where if you look at that the earth system trend and the economic trend, we can clearly differentiate this problem, because all this problem, the population which increased from 2.5 billion to 8 billion in just 70 years after 150. That is why this 150 is considered as a great acceleration period, where all population has been increased, and along with that most of the other activity related to anthrosphere is increasing. So like for example, the earth system carbon dioxide trend is increasing after 150.
Participants are requested to stay back as our speaker is having a small technical error. Kindly stay back. We
Sorry, am I audible now?
Yes, sir,
Yes,
you're
sir.
audible.
You're audible.
Okay, sorry, I was just talking to my screen. I was not knowing I was disconnected. Okay, I will again share screen. Uh, is it visible?
Yes, sir. Yes.
So we were discussing this slide, or where this connection lost.
Yeah, these slides, sir. Androsphere. Yes. Correct.
So this is over, right? Okay. So that is why another geological era came into picture, where it is known as Anthropocene. But if you, I think I have not discussed this slide, right?
Sir, during that time, this slide just started.
Okay. So then if we look at, there are two aspects. Like one is socio-economic trends, and another is their system trend. And that is why Anthropocene. Few people are telling that Anthropocene really started after 1950, but it is mainly because of the social. If you look at the socio-economic trend after 1950, population increased from 2.5 billions to 8 billion. GDP increased like this. Foreign direct investment increased. Urban population increased after 1950. Primary energy use increased. Fertilization consumption increased. Large dams increased. Water use increased. Paper production increased. All this socio-economic activity increased after 1950. That is why it is known as the great acceleration after 1950. If you consider the Earth system, corresponding Earth system trend as well, then we can find that carbon dioxide concentration increased, nitrous oxide increased, methane concentration increased after 1950, stratospheric ozone, surface temperature, ocean acidification, likewise the marine fish capture. So the fish productivity decreased, terrestrial biosphere degradation increased. So that means there is a lot of resemblance between the socio-economic trend and the Earth system trend after 1950. That is why it is known as Anthropocene. But if you look at really, all these 8 billion people are not equally culprit for this. That is why this concept is a misleading concept, the Anthropocene concept. You look at all this crisis has happened due to the capitalistic development forced by fossil fuels. So that is the main reason. We say just the climate crisis or crisis of capitalism. So that is anyway we will get the answer for this in another 100 years, whether it is a real climate crisis or the crisis of capitalism. So that we will get answer maybe in another 100 years. So it is because all these 8 billion people are not equally responsible for this. Only maybe less than 5% of the global population is only contributed to this. Because we are not all are equally not contributing to this. So then, considering that era as Anthropocene, it is a kind of misleading concept, and that's why IPCC came up with a new assessment report. It is clearly telling that human activity is the main reason for this recent climate extremes which we are observing over the globe. So recently in the Californian, as the Californian forest fires, we observed that. And last year also Spain flood, we observed that. And the Kerala, India, everywhere we are observing that. And that is a time where Paris Agreement, which is trying to limit global warming within 2 degree, and then another ambitious limit of 1.5 degrees. So it is not going to happen because the world is moving in such a way. If you look at the last year, 2024, which is the warmest year in the last 120 years. So previous warmest year was maybe 2016. After that, this is going to be the 23 and 24 is going to be the warmest year in the last 100 years. And another thing is that it already bleached that 1.5 degree magic limit, which is being set by the Paris Agreement. So that is why the world is moving at a far faster rate than we envisaged. Because with our climate models, we can project that we were actually anticipating this 1.5 degree limit reaching between 1930, 2035 and 2040, but it happened almost like 15 to 20 years before. So that is why the world is moving at the global warming is happening at a faster rate that envisage we ever envisage. So where we have to think about all these treaties, conference of parties, because conference of parties 29 happened just now, but it also all these 20 conference of parties is not just enough to combat all these global warming issues. So now we have climate models. With these climate models, we can nowadays models are capable of handling the socio-economic data as well. Because earlier the models are just physical models, but now we can include socio-economic activity. Based on that, we can project for the future. If we project for the future with different scenarios, we will end up like something. This is the middle path scenario where we are going to be like 2 degree more warmer compared to the pre-industrial period. So that 2 degree warmer, and if you look at this image, so that is where, as I mentioned in the first slide, we need to know the past climate, present climate, and future climate. So the past will guide us for the future. And if we have through climate models, we have different scenarios for the future. So then based on that, we can devise all kind of short-term and long-term strategies to mitigate the ill effects of climate change. And if you look at the 60 million years back, the Paleocene Eocene thermal maximum global temperature was like 8 to 10 degree warmer. So compared to the present day temperature. So now we are here 1.2 degree warmer. So our projections are telling that by 2300, in another 350 years, the global temperature is going to be something like 10 degree above compared to the pre-industrial baseline period. So what does it tell? During this time, there was the last fifth mass extinction was happened around this period where Earth was warmer at a higher rate of 10 degree more. So a similar situation can be expected in the future as well. So this is a kind of analog situation of the Paleocene heat maxima, and this is going to be our future with the models, projections we can visualize. So based on that, we have to devise appropriate strategies to reduce this present day global warming. So this is how we have to look at the past, present, and the future to devise appropriate strategies for the sustainable strategies for our future generations. So that's why global warming may be another reason for the next mass extinction. It is a combined event, because if you look at the species extinction, amphibians are at the verge of extinction, because IUCN, the International Union for Conservation of Nature, they come up with every year they identify some threatened species and they count it. They found that almost like 30% of the amphibian species is under the verge of extinction. And this is with the projection also, it is telling that maybe 30-40% of the species is going to be extinct. So recently, SDBG, a famous amphibian scientist, he is telling that because amphibian is considered as a indicator taxa, where because the amphibian witnessed all kind of extinction happened in the previous history of the earth. There's only species. So that is why there are a lot of events happening, impacts are there. That's why climate change, when we consider, it is considered as a assessment cycle. It is considered as assessment, it is being considered as a assessment, climate change assessment cycle. It is actually a detection attribution study, because with the data we have to show that something is happening in the recent past based on the data. Based on the data itself, we have to attribute why it is happening. That is why we already mentioned It is happening because of the anthropogenic activities through mathematical models, through physical observations of the Earth climate, and through other theoretical models. We have established that all these recent rapid changes. That scale is very much important. If you look at the previous image, the scale is very much important. This scale is of the order of millions of years. This is kilo years. This is just years. So what is happening in the past over millions of years, that is happening in just a few years. That is the rate at which the present day climate change is more relevant and important, because evolution by nature may not be sufficient for this type of means increased and rapid changes. So once we attribute and we identify the impacts of this, because there are a lot of impacts due to this polar ice melt, glacial melt, global warming, drought, flood, everything is happening. So based on that, we have to devise immediate adaptation strategies and long-term mitigation strategies. So that is the beauty of this climate change assessment cycle. In a nutshell, the impact of climate change can be summarized like this. So, what are the realized changes? The changes in the realized climate, which is seen in terms of rise in temperature, that is uniform all over the world. So everywhere on the world it's uniform. Temperature is increasing, and then sea level is rising. That is, there's two factors which is contributing to lot more melted water from the glaciers is coming to the ocean, and also due to temperature in rise, ocean thermal expansion, the sea level is rising. So both the way, global rising temperature and the sea level rise is the two main linear aspects of climate drivers. And then when it comes to hydrological cycle, it is some places it is hydrology is not directly linearly linked to the temperature increase, because there are a lot of other dynamical factors which determines the rainfall and the hydrology. So that is why the hydrological cycle is getting changed. So in terms of so few regions are experiencing chronic drought situation, another region is experiencing kind of flood situation every year. And maybe in the case of Kerala and all, we are experiencing short-term drought situation in one season, and another season it is a flood situation. So in a year we are experiencing both the end of the extremes, like flood and drought. So that is why if you look at the hydrological cycle, it has got different components like evaporation, starting from evaporation from the ocean water. If global warming increases, ocean water temperature increases, that lead to more and more evaporation. So the evaporated water will be more jump to the atmosphere. So in the case of atmosphere, warming of the atmosphere, every 1 degree warming of the atmosphere can hold additional 7% of water vapor, because saturation vapor pressure is increases with the water with the temperature. So that it can warmer atmosphere can hold more water before saturation. So that is why evaporation increases, the water holding capacity of the atmosphere increases. That means it can hold more water. So when it is condensing, more and more water vapor will be condensing, and this condensed water will form as cloud. This cloud is being carried to the land, and that the higher amount of condensed water will produce extreme rainfall, and that will intercept with the land. It will part of this will go as surface runoff, subsurface infiltration, and the recharging of the groundwater. But all this end up, all this surface flow, everything is end up to the ocean. So this makes the complete cycle that is known as hydrological cycle. So due to global warming, speed of this hydrological cycle accelerated. Hydrological cycle is getting accelerated because more faster evaporation, more faster condensation, more faster extreme events. So more surface runoff rather than infiltration. So that leads to the chance of more flash floods. So this is how accelerated hydrological cycle, and after the rainfall events, the same region will get converted to, will face a lot of kind of drought situations. So this is how we have to actually adapt to this type of situation. So the immediate impact of this is we can see that weather all around the world is changing because Californian fire is example. Even Canada is also getting heat waves. Europe is also getting all the summer season heat waves. It was not that common over this region. Our tropical region is having every year this extreme rainfall events, associated landslide, flooding. So the weather pattern around the world is changing, and the water is also in terms of water. There are two aspects. The quality of the water is deteriorating during a drought period. Water availability is reducing. That will contaminate the available water with a lot of contaminants in the chemical contaminants in the water. So that drought is affecting the quality of the water. Flood is though extreme rainfall leads to flood, but the flooded water is also mixed up water of the sewage and fresh water. So the fresh water quality during the flood time also is under very threat because people will not be getting good water to drink. So this all weather water issue will leads to lot of health issues because most of our health issues directly linked to the quality of the water and quality of the air, because if you look at the air, the composition of the air is getting changed, and we are dumping more and more chemical components to the atmosphere, and also more and more aerosol species to the atmosphere, so that the air quality index, if you look at the air quality index, it is deteriorating even in India, like cities like Delhi and all. So the air quality. So these two, water and air quality problem, end up with a lot of issues in the health sector. It is not just about the physical health. The mental health is also getting deteriorated due to the current nature of this kind of extreme events happening more frequently. And then the ecosystem level changes, we have to consider that as well on the right side. Otherwise, the water health quality and the forest fire, best example is this time the ongoing Californian forest fire, that is also adding lot of issues, and that can we can expect in the tropical region also, like in Kerala also sometimes maybe due to global warming, anthropogenic activities, we can expect that as well. And then the ecosystem level change, because if you look at the ecosystem, any stable ecosystem is mostly determined by two factors. One is rainfall and another is temperature. So that means ecosystem stability is a function of temperature and rainfall, basically the climate factors and the availability of the solar radiation. Once the climate variables, the parameters are changing, the ecosystem also tied to change. So that leads to a lot of biodiversity, loss in biodiversity. So that biodiversity loss is main because it is due to species extinction or the species migration. So species can migrate from a unfavorable climate situation to a favorable situation, so that it can easily migrate. Not the human, which is not able to migrate because due to many other sentimental factors where he is belong to, but otherwise the species can easily migrate to a comfortable region if that climate is changing. So this will add to a lot of ecosystem level degradation that leads to agriculture and food safety, like agriculture system is getting affected and our food security is getting affected. All, and if consider, and then the direct impact of climate change is realized in terms of disasters like heat waves, droughts, storm surges, lightning, landslides, forest fires, drought, tropical cyclones, swirling winds, and storms. So these are some of the impact of climate change. So where we have that is why we have a lot of interconnected pressures between. If you look at the social system, water, energy, and food. These are the three. So all these aspects already I mentioned water and energy, because all this energy need we have to sustain, because for the sustainability of the human system energy is very much required. So that energy system, though we have to move from a highly fossil driven energy, because if you look at the energy budget from where all this contribution of carbon dioxide is coming through the fossil fuel emission or the energy needs, 72% of this carbon dioxide emission is coming from the energy sector, whether it is transport, building, or industry. It is all together is producing around 70, is contributing 72 percentage of this carbon dioxide emission to the atmosphere. So that means if we want to have a long-term mitigation strategy, we need to devise more and more renewable kind of energy sources we have to depend, and then we have to convert from like fossil driven energy from the to the more renewable and green energy. So that energy sector we have to invest a lot, and then the food and food sanitation and water and sanitation, food security, hunger. So these are some of the SDG goals, like SDG goal number 112 and then 6, the water and sanitation. All this is being, all these sustainable development goals are being getting affected due to climate change. So that is why we need to have a integrated approach to deal with this. So that is why, as part of the United Nations, they devised new goals like sustainable goals of 17, and in which the climate action is one of the main goals, one of the spanner which connect to the all other sustainable development goal. If you look at the 169 targets, 67 targets associated with all these goals, it is directly linked to climate change, because climate can affect all other targets and goals. So that is why climate action is considered as the main tool through which we have to fix all other sustainable development goal. Another way we can say that climate action is the central uh, activity of the sustainable development goal. So that is why we have to sustain this, and there is no quick fix or bullet, silver bullet. Like for example, the ozone problem that we fixed, almost fixed. But otherwise, in the climate change or global warming problem, like that, there is no quick fix or the tablet is available. So we have to do it through many activities, like global population is reducing. There's already, I mentioned all this, and the main climate action plan should be linked to the emission reduction. That is a long-term mitigation strategy, and then the adaptation strategy, like how we can adapt to the disasters, and then the community engagement. That is very much important. This should be the main plan of action for a sustainable climate or the sustainable future. So where climate action or integrated climate action is very much essential to deal with this in terms of mitigation and adaptation. So I think I have done with the talk, and we can discuss if any doubts. I will stop here. The presentation I am stopping. We can have discussion.
Thank you, sir. Participants are kindly requested to unmute themselves or use the chat box to ask any questions, sir.
Sir, I have one question, sir.
Yes,
sir,
please.
Can you hear me, sir?
Yes, please.
Yes. Sir, how actually these climate models, as you discussed some climate models, so how these climate models can be calibrated and validated, sir?
Can you please introduce yourself so that I will get an idea of your background?
Sir, actually myself, Suraj, sir.
Okay. So the climate models are it's a physical models. So there are a lot of uncertainty associated with the formulation of the models, because these models are built based on the physical laws. Basically, and it derived from the Navier-Stokes equation, but otherwise the variants of Navier-Stokes equation, like a momentum equation, thermodynamic energy equation, then equation of state, and equation means water vapor conservation equation, mass continuity equation. So these are the 7 fundamental equations on which we built climate model. But the thing is that there are a lot of uncertainty and unknown physical process which is not able to resolve or solve. So that part is the main contribution of the errors to climate models. And then this is partial differential equations, as you know, the uh, momentum equation and all. So these partial differential equation, there is no analytical solution. The exact solution is not available due to the unknown nature, a non-linear nature of the equation. So we have to solve it numerically. That is why it is known as numerical weather prediction or numerical climate models. So numerical values we are solving. So in that also we do a lot of assumptions like subgrid scale, unresolvable process. We assume with the empirical relationship. So that adds a lot of uncertainty in the model. And this partial differential or the finite difference equations, they are solved. It is a initial value problem. So there a lot of data is required, but that data is not enough to initialize the model. So these are the some of the source of uncertainty to the climate or the weather models. So the weather prediction and climate prediction is entirely two different approach. Like weather prediction, we are predicting for the next 1 day, 2 day, or maximum 1 week. But the climate is actually a projection. So where we need to know what we don't know what is the future. So then that is why we devise different type of scenario. Based on the scenario only we will be, because the future scenario it is a like in front of us there are four different pathways. Which pathway to select, that depends on this climate model projection. So we force, that is why especially we for the future forcing we simulate this model with the future expected forcing. So that is why there are a lot of uncertainty. I have already shown that shaded region is the uncertainty cone. So there are a lot of uncertainty, but you have to deal with those uncertainties. So and we calibrate the models based on the past data, because we run the model not for the future, but we do hindcast, because the already happened events we run. Because like for example, when we develop a model, we run the model not from it's a normal AML model. Also we use means training data part of say 70% training, 20% testing, and maybe one 10% evaluation. Like that, we done all the model for the last 50 years, and we evaluate the skill of the model, compare with the actual observation which had happened in the past. So we make some adjustments, calibration. We calibrate the model with respect to past data, available data, and then based on that calibrated model, we are giving the forecast for the future.
Yes, sir. Thank you. Thank you, sir. Thank you so much.
Are there any more questions from the participants? I think it is a no, sir. So let us conclude the session. I kindly welcome Dr. Suraj Rajan C for the vote of thanks.
Yeah, thank you, sir. Gave a detailed explanation about the rise of global temperature and effects, how the heat is dissipated and how the ocean heat content contribute to the warming of atmosphere. Detailed explanation has given. Thank you, sir, for coming online and deliver a session for us in AICTE ATAL FDP program. Hope that all the participants received a very good technical understanding about climate science and models. With a token of gratitude, Department of Chemical Engineering, Amaljodi College of Engineering, sharing a virtual memento to you, sir. Thank you so much, sir.
Okay, thank you.
Thank you, thank you, thank you.
Okay. May I leave?
Yeah, yes, sir, yes. Yes,
Okay.
sir. Thank you
Okay.
so much, sir.
Thank you.
Thank you, bye.
That brings an end to our first session of the third day of FDP. We'll be continuing with the next session shortly. Our next session is titled Increasing Flood Threat Due to Climate Crisis and Developing Flood Resilience with Community Participation.